Hey, welcome to the solutions to the spring break multiple choice homework. It's very important that you listen to this slide or at least read it. I want you to take the test before you look at the answers. The idea here is you're getting ready for a real AP test, and it's not going to do you any good to help yourself along by looking at each question's answer as you go. So take it, then come back, then watch the answers. When you're done, score yourself and do an honest job. So if you sincerely meant to write something but you wrote the wrong thing, you got it wrong. You have to treat yourself the way you're going to be treated by the scoring machines, or there's really no point in using this as a proxy for your readiness. Lastly, when you're done, just send me an email. Tell me how many you got out of 35. And be honest, it's not going to hurt you in any way. I just want to know.
Starting from question 1, this one's pretty straightforward. You just have to notice that in the prompt it tells us question 2 is an elastic collision problem, which means they are relative speed, linear momentum, and kinetic energy. Now real fast, remember linear momentum, this second bullet point, that's conserved in all collisions, regardless of whether it's elastic, inelastic, or completely inelastic. Relative speed and kinetic energy, however, the first and third bullet points, are only conserved for elastic collisions. I want to show a formula for each of these three ideas that basically says the same thing with symbols that we wrote in words. So if the relative speed is conserved, what would that mean? Well, it would mean that the speed that one object either gets getting closer to the other or further away from the other is going to be the same before and after the collision. So we could say that the velocity of A minus the velocity of B, in other words, their difference in velocities before they collide, is equal to the velocity of B after, and that's what the prime notation means here, minus the velocity of A after. And we inverted the subscripts, right? So it's B minus A as opposed to A minus B. What does that mean? That means that if initially the two objects are getting closer together, after the collision they're going to be getting farther apart, and vice versa. Linear momentum is conserved. We've used this formula before, so I'm not going to walk you through it. And finally, kinetic energy is conserved. Again, we've seen as it turns out we really only need these two formulas for this question, but that third one, the kinetic energy, can be useful in other problems. We can also eliminate a lot of stuff here because A is equal to B, or more accurately, the mass of A is equal to the mass of B. Because all of them had 4 kilogram masses, we can cancel all of the m's, and we're... So we have these two expressions. Let's try to clean this up a bit. In the prompt, we're asked to figure out how fast the block on the right, or in this case, the one in the middle if you're considering all three blocks, how fast is it moving after the collision? Symbolically, that would mean I want to instead show you that it's more useful to find velocity prime of A. Here you have those same two equations. I've just put them side by side so it's easier to see what's going on. And we also know that VB, which would mean the velocity of block B before the collision, is 0. So we're just going to plug in some zeros here and clean this up a little bit on both sides. We're left with two equations that are both already solved for V sub A, which means the velocity of block A before the collision. And that means that the expressions for VA on both sides can be set equal to each other. They have something in common. They both have a positive V prime B, so I'm going to subtract that from both sides, and my result is V prime A is equal to negative V prime A. What does that mean? That means that there must be some number, some possible number here that is its own negative. What's the only number that is equal to the negative of itself? So I'm sorry to keep you in suspense any longer, but it's absolutely imperative that you don't misapply what I'm about to say. This result is only true if two preconditions are met. So the first of them, if and only if, that's what the two F's mean here, if and only if. I don't know if you guys knew that. If and only if two objects have the same mass, and if and only if they collide elastically, and in this problem both of those conditions have been met, then the result, now we can apply this trading speeds idea because these two blocks, the ones that are about to collide, have the same mass, 4 kilograms, and because this collision is elastic, it says in the prompt, they're going to trade speeds, which means the block on the left will take the initial speed of the block in the middle, and therefore its final velocity is 0 meters. You can extend this now because we know the initial velocity of the center block after the collision. So here's kind of what that might look like. So these two blocks collide together. We're going to find their combined velocity v prime after the collision. For this, we use momentum conservation. So the momentum of each block individually before the collision is equal to their combined momentum after the collision. Because the block on the right, which I'm calling block C, had no velocity, it doesn't have any momentum before the collision, and therefore the entire momentum before the collision is just in block B. So that's 4 kilograms times 6 meters per second, and the combined mass of the two blocks once they stick together is 8 kilograms, giving us a final velocity of 3 meters per second. One last note on this. It's really just a proportionality question because we double the amount of mass that was in motion from 4 kilograms to 8 kilograms, the total velocity of the system halved from 6 meters per second to 3 meters per second. Question 4 is pretty straightforward. It's a calculus question. We're asked to find the net force, and the formula for net force is just sum of forces equals ma. That's Newton's second law. We don't actually know m, but we're just going to leave it as m because it tells us in the prompt up here a particle of mass m. So that just stays as is. A, however, we have to figure out, and you almost always get a point on the free response if you tell the scorers what you're doing in terms of the calculus. So in this case, I'm going to go from a function for velocity given here in the prompt. I'm going to go from this function to the acceleration by taking the time derivative. So this is usually worth a point in the free response. Obviously, it won't be worth a point in the multiple choice, but I just want to make that apparent. Anyway, I'm taking the time derivative. This is just power rule, and b and c are both constants. So c is going to turn to 0, and we're going to bring down that 2, put it out in front, and lower the power by 1. So my acceleration at any time is 2bt, which means the acceleration at time t1 is just 2bt1, and my final answer is the mass times 2bt1, or answer choice. Question 5 is a proportionality question, but it can be done with kinematics. Starting with the kinematics way. So let's first just identify the time intervals we're analyzing. Initially, we start at rest at time 0, and then we know some information at time 1 second. So I'm going to use that interval first. And kinematics tell us that the position at time 1 is equal to the position at time 0 plus VOT plus 1/2 AT squared. We already know x0 and v0 are both 0, so this is really pretty simple. Position at 1 is given to be 1 meter, 1/2 a time change is 1 second, t squared here, and so you get an acceleration value of 2 meters per second squared. I can now use that value to try to figure out what the question wants, which is the displacement from time 2 to time 1. So I'm going to use the same formula, but note how the subscripts have changed. We're no longer going from 0 till 1. These subscripts refer to the time in question. We're going from 1 to 2. That's the interval we now care about. I'm going to subtract that x sub 1 to the left, and that's going to give me the displacement, delta x, for this interval, and that cleans up to v sub 1 times the change in time. Now, note what happened here. Even though we end at the time 2 seconds, this is not t. This is not t final, it's the change, and so I use 1 second because that's the change from 1 until 2. 1/2 a is the 2 we just found a moment ago, and then t squared, and we end up with. I'm going to go back to that first interval here and see if I can find v sub 1, because if I know that, I can just plug it in and then solve for delta x. So, starting from kinematics, I'm going to use this one because it seems simple and we have all the information we need. The initial velocity at time 0 is 0. We know the acceleration, and we know the change in time is 1. And we find that at the moment 1 second has passed, and plug it in here for the velocity. Oops, didn't need to do that part. But anyway, plug it in for the initial velocity, or velocity at time 1, and solve for delta x, which. Here's the other way you could have done that last question, just with the proportionality. So from the same kinematic equation we just used, you know that the position of an object is proportional to the square of its time. And that's actually true for all objects that are accelerating uniformly. Therefore, if you travel 1 meter in 1 second, basically we're saying that in 1 second you've traveled 1 squared meters. Then how far do you travel in 2 seconds? 2 squared meters, right? But that doesn't give you the displacement from 1 until 2 seconds. It gives you the displacement from 0 until 2 seconds. So to get the total, the answer to the question here, it's hard to explain how question 6 is solved without seeing what's going on here. So I googled. So let's imagine for a moment that we've got this boat. This is a bird's eye view. Why did this happen? So he doesn't go from A to B, he goes. What if the captain tried to aim somewhat upstream? Would it be possible? Yes, it is absolutely possible. But, so I'm going to take that boat, and I'm going to say that a component of its velocity must balance out the river current. So in this question, the total velocity is going to be angled partially towards B and partially upstream, and that means that the component down here must. So here's that same boat, and he's going to try to do this. His total speed, his maximum speed, is 5 kilometers per hour. But if he angles upstream, then that means the 5 kilometers per hour is the hypotenuse of this right triangle, and the component of the boat that is, or I'm sorry, not the boat, the component of the boat's velocity that points upstream is going to be less than 5. Well, what if the captain tried this? Could he just aim perfectly upstream? Yeah, he could, and then his velocity would be exactly the right amount, 5 kilometers per hour, that he could balance the current of the river. But then there's no component of his velocity aiming towards B or across the river. So the best this captain can do is to not go downstream, but he cannot cross to point B. Question 7 is actually a lot more simple than it might seem. So let's redraw these vectors a little bit bigger. You start with v1, you want to end at v2, and it asks you for the acceleration. Well, the acceleration is just the change in the velocity. So what vector would you have to add to v1 to get v2? So let's just set this up like it's a vector addition question. You might be confused by the way I've actually shown this, because normally we do tail to tip, and these are not tail to tip. These both originate at the same place. The reason I'm doing it this way is because when we do tail to tip, we usually don't know the resultant. We don't know the final answer, which is what v2 is here. So this is actually going to be tail to tip in just a second. v1 is the first vector, and then we have to add some vector to it so that the final of the two, the sum of those two, is this v2 vector straight up. And therefore, tail to tip does work because the unknown. Okay, so I've worked this question 4 times, trying it different ways. So I first defined this k, which is in the question, as 1/2 mv squared, and I'm using the subscript 1 to mean the bullet. And then I use momentum conservation to figure out how fast the gun is going to be moving. So you solve this for the velocity of the gun. That's my 2 subscript. And you get negative m1v1 over m2. I'm going to now find the kinetic energy of the gun. So 1/2 mv squared with the subscripts of 2. I'm going to plug in the expression for the gun's velocity here from this third bullet point. Plug that in for velocity 2, and then square it. And then I'm just going to remove the square outside the parentheses. I just squared everything here. So you're going to end up with an m2 over an m2 squared. That cancels out. And I just move this 2 from the 1/2 into the denominator. And you have m1 squared v1 squared over 2m2. And remembering that k is 1/2 m1 v1 squared, I'm going to factor 1/2 m1 v1 squared out of this expression to see what the multiplier is on that k value. So here's that k, right? And if I'm not mistaken, all that's left over is m1 over m2. But it's this. It's answer choice D. I don't know why. So this is a really straightforward center of mass question, and you actually don't have. Here we have a really simple projectile question where we have a known velocity and a known angle. First thing to remember is that at the maximum height, we know that the instantaneous velocity of any projectile is 0, so we're going to use that information here. The other thing to be conscious of is that the 200 meter per second velocity is not in a single dimension. It's got to be broken up into its x and y components. And therefore, when I go to do kinematics, you have to only use the component of the velocity in the y dimension, and therefore 200 sine 30, not the entire 200. So I'm going to sub that in, and 200 sine 30 is just 100. 100 squared is 10,000. And I'm going to subtract that 10,000 to the left side, divide both sides by negative 20, and we get a. Question 11 tells us right in the prompt we have a non-constant acceleration, and as soon as you either. So starting from a equals 12t, I'm going to take the integral with respect to time and find that the velocity function is 6t squared plus c. In calculus, you'd say plus c. In physics, that c means the initial velocity, but the prompt tells us that it starts from rest, and therefore we don't have to include that. Let's integrate one more time. So the integral of v dt gives us the position function, which ends again with plus c, which is the initial position. We also know that to be 0. And we finally evaluate. Here in question 12, we're asked to consider what happens as a figure skater who's spinning brings her arms closer to her body. All right, this question you don't know how to do yet, so I'm sorry, but this is a. Here, number 14 gives us a really straightforward calculus question. We're asked to find the instantaneous. Question 15 is sort of the opposite of question 14. Instead of being asked for the acceleration. All right, so here in question 16, we're asked to evaluate a pendulum where the ball starts some height. Let's just first think about what sort of things might be valid here. For starters, we can't use kinematics because this object is going to be experiencing a changing acceleration. We can, however, use the energy conservation approach, but that might not be apparent. The reason that it's valid here is because the strategy of energy conservation can be used anytime that there is no work done by non-conservative forces. And at first glance, you might think, well, there is a non-conservative force here, right? The tension in the string is going to exert a non-conservative tension force. That's true. It does exert a non-conservative force, but it doesn't do any work on this system because the angle between that tension, which is centripetal or towards the center, and the instantaneous velocity vector, which is always tangential, is 90 degrees. And so since the formula for work has the cosine of the angle in there, cosine of 90 being 0, centripetal forces do no work, and therefore energy is conserved. So let's use energy conservation. First thing to think about is because the string length is L, when the ball reaches the lowest point in its swing, it's down a total distance of L from the pivot. That doesn't mean it's descended L, because it didn't start all the way up here at the top. So let's see if we can figure out how much distance the ball travels vertically from the release point to the bottom. I'm going to construct a right triangle here, and we can now use the L as the hypotenuse, the length of the string, and the angle given to say that the component acting on the left side is given by L cosine theta, and this component is L sine theta. What does that mean? Well, it means that if the entire length of the string here is L, and this much of the string is given by L cosine of theta, which is cosine of 60 degrees, then this delta y, the actual distance the ball descends, is going to be given by the expression L minus L cosine of theta, or again, that would be cosine of 60. You can simplify this immediately if you like. Because the angle is 60 degrees, the cosine of 60 is a half, so you basically just have L minus 1/2 L, so this would just be 1/2 L, but I'm not going to do that just yet. We can factor out an L here. You don't have to, but I like to do that whenever there's a common term. And now I'm going to use energy conservation. So this is saying that the initial gravitational potential energy before the ball is released, that's here at the top, or the highest point in its swing, is equal to the kinetic energy at the bottom. What is the assumption here that I'm making? The assumption here is that the y equals 0 point, which I did not draw on the picture, is at the lowest point in the swing. Remember, you can set that anywhere you want. And by setting it at the lowest point in the swing, I can say that there is no gravitational potential energy down here, and all of the energy is just kinetic. We lose those m's because they're on both sides in the numerator. And I'm going to now replace y with our expression for y above. Now you'll notice this says y, and this says delta y. Why is that sort of the same thing here? Well, because delta y is the final y position minus the initial y position, but the final y position is just 0, right? Like it ends at the point 0, as I just said. So the entire change in y is just given by the initial y position. So GL times 1 minus cosine of 60 is equal to 1/2 v squared. We can now solve this for v, and you way of getting at the idea of the work energy theorem. So that is the theorem that states that the sum of all of the works done by all of the forces acting on an object is equal to the change in its kinetic energy, delta K. That's useful here because we're asked to determine the change in kinetic energy and what it's equal to. Well, the answer is the net work. That's not directly an answer choice, but what is the net work? Well, it's the work done by the net force. So your answer is just A. So I love this question because it might look at first glance like you don't know how to do it. It mentions simple harmonic motion, and it's true that we haven't learned what that is yet, but you don't have to know anything about simple harmonic motion. Look what you have. You're starting from a position versus time graph, right? And you're trying to find a graph that shows kinetic energy. All right, well, think about what we know. Kinetic energy changes as a function of velocity. And so what we really care about is not this position time graph, but the velocity time graph that would correspond to this. So we just need to take the derivative, and the graph of what looks just like the sine function is the cosine function. So you might have been tempted to choose answer choice A here, because this is the correct derivative of this. However, that's wrong only because in the formula for K, for kinetic energy, you square velocity, v squared. And therefore your answer cannot be negative. You can never have a kinetic energy down here in quadrant 4. So all we do is instead take this partial parabola in quadrant 4 and it flips vertical so that all of the energies are positive or 0, and therefore the answer is B. So this one's a little bit different from the last one, although we do start with the same image, this position versus time graph that looks like a sine function. But we're asked to figure out what the graph looks like, not as a function of time, but instead as a function of position. So we need to figure out what's going on at different positions, which is on the y-axis here in the first graph. So let's just try to pick a couple of points that look important and try to match them to a corresponding graph down below. So for starters, it's good to look at maxima and minima. So we'll go to this maximum position here. This is the highest position we ever get in the positive direction. And at that moment, the slope of the tangent line is instantaneously 0. So what that means is when we have the most positive position, and as it turns out also when we have the most negative position, we have a velocity of 0 and therefore a kinetic energy of 0. So that immediately gets us to answer choices C and D, both of which show a kinetic energy of 0 at the least and most position values, the most negative and the most positive position values. So we need one more point. To do that, we will go to the center. That's kind of where they have a big difference. This graph, graph C, shows that at the center, when position is 0, we should have a maximum kinetic energy. And this one says that at position 0, we have a 0 kinetic energy. Well, coming back to this, let's just go to position 0. That's given here. And at this moment, we have the steepest slope anywhere along the graph. I mean, sort of tied for the steepest, right? It's also the steepest here in the center and here at the end. Those are all the same. But at position 0, we should have the maximum slope and therefore the highest velocity and therefore the highest kinetic energy. So the correct answer is C. Here in question 20, we're asked to look at a situation where something is orbiting something. Well, the first thing to consider here is there is no external net torque. You might think there is, but there isn't. And the reason is that the only force acting on a planet or a moon or anything that orbits is the gravitational force from the center body. In this case, this is the sun, and this is a satellite. X is a satellite, or at least when it's at position X, this little dot here is a satellite. So it's always going to be acted upon by gravity, but that's only a radial or centripetal force, meaning that the angle between the instantaneous velocity vector and the net force vector will always be 90 degrees. And therefore, because of the equation, we're going to say that there's absolutely no work done. And in other words, there's no external net torque on the satellite as it orbits. But what we do know is that because of Kepler's laws, this is going to speed up as it gets closer to the sun and reaches y. That's probably when it's moving the fastest. And then it's going to slow down as it approaches x. And even though it has different speeds, it also has different radii, right? So like consider for a moment, look at this x, this position x. The radius is huge with, compared to this other one. So the other radius from the sun to y, that's very small. And that means that even though they have different radii, they also have different speeds, and they're proportional to each other in a certain way. And so we say the answer is that the angular momentum remains constant because there are no external net torques, but the speed increases from x to y. Back to our universal gravitation unit, which we did as part of our circular motion unit. We've got this new planet, and its mass is 4 times larger than the Earth. Before we do anything else, let's just think about what that would mean. Here we're looking at 2 different satellites, and the difference between them is that one is twice as far away from the Earth as the other, and we want to figure out how their accelerations compare. So to do this, we're first going to need an expression that has the acceleration of a satellite in it, and because the only force that acts on a satellite is the gravity, I'm going to use the expression for gravitational force. Turns out, though, that there's 2 expressions. One is gmm over r squared, which we used in the last question. The other one, the more common one that we learned at the start of the year, is mg, little g. But that g, little g again, is not 10 everywhere. This is sort of like g local, or the acceleration of gravity at any given position. So these satellites have a local value of g that is significantly less than that at the Earth. We do have a lowercase m on both sides. This means the mass of the satellite, so the answer will be independent of that. And that means that the acceleration of any satellite is given by gm over r squared, where m is the mass of the Earth and r is the distance of the satellite from the center of the Earth. So if one satellite is twice as far from the Earth as the other, then you will put 2r in the denominator for one of them, and because you're squaring this value, the acceleration of the farther away satellite is 1/4 the acceleration of the closer satellite. Question 23 is really a straightforward energy conservation question, but you have to account for the fact that the ball is moving both translationally and rotationally. Probably be easiest to show this so we can kind of visualize what's going to happen. So this ball is originally rolling without slipping on the ground with some speed v, that's a translational velocity, and then it's going to roll while decelerating up this ramp, and it's going to reach some maximum height and then roll back down. Right now, at the bottom, it's got translational and rotational kinetic energy. And then once the ball gets to the top here, it's got gravitational potential energy only. At this instant, at the highest point, it has come to rest before it begins rolling back down. So let's try to figure this out, starting from translational and rotational kinetic energy and ending with gravitational potential energy. Formulas for each of those things given here. And the inertia of a sphere, as it says, is 2/5 mr squared. So I'm going to replace I in the second line with 2/5 mr squared. And omega, I'm going to replace with its equivalent, v over r. So that way we only have one velocity term, just v, no omegas present. We're going to end up canceling a lot of stuff. You end up with an r squared over r squared. That goes away. And there's an m in each term, so those all go away. And if you solve this for h, you get 7v squared over 10g. All right, this one actually gave students a little more trouble than you might expect. The reason, well, let me not get ahead of myself. So the first part here is at point Q, what direction is the acceleration? Remember that when something moves in a circle, there's two different directions that it can be accelerating, or more accurately, there's two dimensions. It can accelerate centripetally, and it can accelerate tangentially. Centripetal acceleration, or center-seeking acceleration, makes you turn. Tangential acceleration makes your speed change. So let's figure this out. At point Q, we're at the lowest point in the path. Well, what happens from P until Q? The ball is descending, and due to the force of gravity, it's going to be speeding up, speeding up, speeding up. Then it gets to Q, and then it starts ascending, and it's slowing down, slowing down, slowing down. At the instant it reaches the lowest point here, it has stopped speeding up and not yet begun slowing down. So the acceleration is entirely centripetal, not tangential, and it always points towards the center of the circle. So the answer for Q is upwards, towards point O. How about at R? Well, at R, it is at the same height from which it was released, P. And because it was released from rest at P, once it gets back to that same height, it must be at rest again. So if you're at rest, you are not moving in a circle. So therefore, there is no centripetal acceleration at R. So is there any tangential acceleration? Is the ball's speed changing at this instant? Yes, and it might not seem apparent why that's true, but it's the same problem as if you throw a ball vertically upwards in the air. At the moment it reaches its apex, its velocity is instantaneously zero, but there is still a gravitational force that is not balanced, and your forces have to be balanced in order to have a zero acceleration. Because that is not the case, it is accelerating through point R in a downwards direction. The answer here is C. All right, so as this car moves from point X to point Y, what do we know about it? We know it's turning, and when anything turns, it must have at least a component of its net force, if not all of its net force, pointing in the center-seeking, or what we call the centripetal direction. If you don't have that centripetal force, you cannot turn. So we're going to already eliminate three answer choices. This cannot be B, because the force is tangential, cannot be C, because that makes no sense, the force can't point away from the center, and it cannot be E, because again, the force here is tangential. That leaves A and D. Which one of them is correct? Well, what is the relationship between some of the quantities involved here? F equals ma, right? F equals ma. And therefore, the force always, in every problem forever, will point in the same direction as the acceleration. There will never be a problem where that is not true. So the only of the remaining choices, the only one where that is the case is in D. Just because it's useful to point this out, in D, the force is not entirely centripetal, is it? I mean, this is the centripetal direction, sort of. I'm not drawing it perfectly, but pretty close. That means that this net force has two components. So it doesn't ask you here to answer this, but if it had said, describe the motion of the car at the position shown in answer choice D, you would say that it's turning because it's got this centripetal net force component here. but it's also speeding up because it's got this net force component in the tangential direction, sort of. This question is a simple harmonic motion question, so you probably couldn't solve it. Don't feel bad. It's not something that you've learned yet. But I do want to just show you how to solve these pretty simply. As it turns out, these formulas, this x and this y formula, oh man, look at that line. That is perfectly horizontal. I'm not going to do it again, am I? Almost. Anyway, these formulas are always written in the same general format, which is that x is equal to x max, in other words, the largest displacement, times some trig function. So this could either be sine or cosine. I'm just going to write sine for now. Sine and cosine are the same curve, right? Just shift it, so it doesn't matter which one you write. Times omega times the time value. And then there's one other thing, but it's not relevant here, so I'm going to omit it. What that means is that from the formulas, you have all the information you need to solve for the period, because this first term in front of the t must be omega. So that's 3 in both cases. Well, what is omega? Omega, as we learned in our rotational motion unit, is the angular velocity. So if I set that up, how fast am I moving angularly? It's the number of radians in a circle divided by the period of a circle. T, capital T for period. So if I rearrange this just to find the time, we would determine that the period t is 2 pi over omega. In other words, 2 pi over these 3's. So 2 pi over 3 is the correct answer. So here we have the same two position functions from the previous question. It's just that they're broken up by dimension. One is x and one is y. So how do we go from position to velocity? Well, we know that for starters, if I want the total velocity of something, it's just the vector sum of the components in each dimension, right? And remember, when you're adding vectors, you have to do it using the Pythagorean theorem. So we don't always write the square, but this is just c squared equals a squared plus b squared. So we need to first find those two values, v sub x and v sub y. To do it, we take the derivative. So the velocity in the x dimension is just the time derivative of that function in the x dimension. And this is the chain rule thing. So we need the derivative of the inside times the derivative of the outside. So the derivative of 3t is 3. The derivative of 5 cosine theta is negative 5 sine theta. So the total is negative 15 sine 3t. Same in the y dimension. I'm going to take the time derivative of 5 sine 3t and get 15 cosine 3t. And now we can use those as our two expressions for vx and vy. And again, this is a Pythagorean theorem thing. So I'm going to take the square root of vx squared plus vy squared. And you'll notice something really easy happens if you know your trig identities. You have a sine squared theta plus a cosine squared theta. Well, what is sine squared plus cosine squared? It's 1. It's just 1. And that means that we end up with 15 squared times 1. Square root of 15 squared is just 15. All right, so here we have a question asking us to determine the acceleration of an astronaut that's a certain distance above the Earth. And we're going to start with those gravitational force formulas. So if you remember from a few questions ago, there's two formulas for gravitational force. One is the universal formula, gmm over r squared. And that's usually your best bet because it's always true. The other one is m, lowercase m, meaning the mass of the object in question, times g local, where g local is the acceleration at that point. Unfortunately, neither of these formulas can be used immediately because we don't have enough information. What you can do is say that since these are both expressions for gravitational force, you can set them equal to each other. The m cancels out, the little one, and you have an expression here for g local. And that's what we're looking for, right? G is the acceleration due to gravity. You can now solve, if you have stored or have memorized, the universal gravitational constant and the mass of the Earth in your calculator or in your brain. Since I assume most of us don't have that information at hand, they don't expect you to do it that way. Again, though, you can and you get the same answer. What are we actually changing? What's the difference between this satellite if it were on the surface of the Earth or 300 kilometers above the surface? Well, would g change? No, that's just a constant. Would m, the mass of the Earth, change? No. Only r changes. The only thing that changes is r. And as it turns out, The only thing that changes about r is that we've gone 300 kilometers higher. Well, 300 kilometers is a 5% increase in your radius, right? It says in the question that here on the surface of the Earth, the radius is 6,000 kilometers. Another 300 isn't that much. It's a 5% increase. And since everything else is a constant, you can just say that the acceleration of this satellite is the acceleration here at Earth divided by 1.05, which is a 5% increase on Earth's radius, right? Squared. Squared because it's r squared in the denominator here. And that ends up giving us 9.07 meters per second squared. And so the answer choice that you should choose is 9. Here in question 29, we're asked to determine the force that one block exerts on another block. And there's also this external force of 20 newtons that's pushing. The first thing to think about is that we can discard some answer choices immediately. So we want to know the force that the 2 exerts on the 3. And that means if your system is just the 3 kilogram block, the 2 is being on the right of the 3 is going to push to the left. So we can immediately discard any answer choice that doesn't say the force is to the left, meaning B and D. All right. It's been a little while. It wouldn't hurt to review. There's a general strategy that you should follow for any multiple object system, and it is this. You should always begin by focusing on everything together and use them to find the acceleration. So in this problem, that will mean both blocks at once. Then, after you do that, you want to narrow your focus to make the force that you're looking for external. So here's what I mean by that. This is the system, at least to start off. And in the 2-block system, the force that the 2 blocks are exerting on each other, given sort of right here, this is the normal force, would be equal and opposite. The force the 3 exerts on the 2 is the same in magnitude as the force the 2 exerts on the 3. And so you couldn't solve for a force if it's internal. So we're going to begin with the 5 kilogram system and find the acceleration. Sum of forces on both blocks together is 20 newtons to the right, nothing to the left because there's no friction, and that would equal ma, where the mass is the mass of the 2 blocks combined. Solve for a, we get 4 meters per second squared. So what is that the acceleration of? That's the acceleration literally of the 2-block system, but they move together. So they have the same acceleration individually as they do as a group. In other words, this is also the acceleration of each block, right? That's why we start by looking at everything, because now you know the a value even if you... So this time we're going to narrow our focus to just the 3 kilogram block because the question asks us to find the force that the 2 exerts on the 3, and therefore on the 3 gives us the system as the 3 kilogram block. So what forces are acting? Well, the 20 Newton force does act on the 3, it's touching it, and then the force from the 2 kilogram block, as we said a moment ago, is leftwards, right? It's on the right of the 3, so it's pushing to the left. So we solve using the same acceleration from the last slide, and we get a force of 8 newtons, and that acts to the left like we already said. All right, here in question 30, we're asked about the period of oscillation of something that's on a spring, and for this we go to our equation sheet, which gives us the period formula. And that formula is 2 pi times the square root of mass over k, k being the spring constant. So let's just try to figure out what's proportional here. For starters, 2 and pi are both constants, so I can take those out. And the period of something on a spring is proportional to the square root of its mass over the spring constant. That's not good enough. That's not an answer choice. So we need to go a step further. Starting from the sum of forces, the problem tells us that when you hang a certain mass, mass m, on the spring, it will displace it a distance d. At that moment, we would say that the spring is exerting a restoring force that is proportional to its displacement. That's just given by Hooke's law as negative kx. Remember, k is the spring constant, and x is how far that spring has been stretched from its equilibrium position. Well, the negative sign in Hooke's law is only there to tell us that the force a spring exerts is always in the opposite direction of the displacement. But let's think about what the directions are in this problem. You hung a mass on a spring, the spring went down. That means that the force, Fs, is pulling upwards. So using the convention that gravity is down, or vertically downwards is negative, and upwards is positive, we're going to say our restoring force is positive, and that's why I made it positive up here in my sum of forces. So the spring pulls up, gravity pulls down, and they are balanced. Therefore, the spring force, or Kx, is equal to the gravitational force, and I can now solve this for, oh, I'm actually getting ahead of myself. We're not going to solve just yet. First, we're going to replace x, which is the displacement. The spring has been moved from equilibrium, with d, because that's how far the problem tells us the spring was displaced. So it's same meaning, different letter. Now I'm going to solve this for k, and it is mg over d, and I'm going to use that expression over here. I'm going to replace my k with that. So we end up with an m over an m. Those are going to cancel. And then we get 1 over g over d. And that, using a little fractional math, gives us a proportionality of the square root of d over g. And that is answer choice A. Here in question 31, we're asked to match a torque to a torque from a starting point. So we need to first know the torque that is acting on this, the first image. So let's use the formula for torque, Rf sine theta, and it's useful to review what those terms mean. So R is always the straight line. That's not a very straight line, but anyway, it's a straight line from the pivot, which is marked X here, out to the place where the force is applied. So that's a distance L. So where this says R, we're going to substitute an L. F is the force, and theta is the angle between R and F. In this case, that's a 90-degree angle. Sine of 90 is 1, so we're looking for a torque that matches LF. That's our goal. Let's see if any of these have that, or there's answer choice E, none of the above. Starting from A, we know that the R value is the distance from the pivot out to the place where the force is applied. So that's L. We also know that the force in this case is 2F, and it's in the same direction. So what's the angle between them? 0 degrees. They point in the same direction. Sine of 0 is 0. We have no torque. Answer choice B. Distance is only L over 2 rather than L. Force is still F. Angle is still 90. So that means we have a torque of 1/2 LF, not a match. Answer choice C. Here's where it gets kind of interesting. So a lot of people are tempted to say RF sine theta. Okay, so L is the R value. That's correct, by the way. F is 2F. That's correct, by the way. And sine of theta is the sine of 60. And that's the mistake, because you always plug in the angle, not just whatever it says in the picture, but the angle between R and F. So this whole angle here, this whole angle is the angle you want to plug in. And we know that 60 is the angle between the 2F and the vertical, but there's also a right angle here. So, I don't mean to be drawing. Why is it still drawing? Oh, sorry about that. But anyway, we know the total angle then is 150 degrees. And that gives us the same torque as the prompt. Answer is C. So let's find an expression that relates energy to force. Starting from the expression we had in class a few weeks ago that the work done by any conservative force is equal to the negative of the change in the potential energy, I'm going to replace the work done by the conservative force with the expression for work, and this is the one that's always true, remember, the integral of f of x dx, whereas you can use f d cosine theta only if the force is constant. This is always valid. Let's rearrange that a little bit because we want to solve it for the force. That's what we're asked to evaluate. And really, this just gives a very simple answer. We needed to take the derivative of the position function with respect to time. Well, here was the position function given in the question. This is just power rule. Take the derivative, and you get 12x minus 4. Now notice that the negative sign never went away. That is still present, and that's going to be important because the question asks us which direction the force points. Evaluate this at position x equals 3 meters, and we get negative 32 newtons, and that means the answer is B, 32 newtons in the negative x direction. Here in question 33, we're looking at a very, very straightforward projectile question. Because both balls start with an initial vertical velocity of 0, they will take the same amount of time to hit the ground. So let's start off by finding the amount of time it takes for them to hit the ground, and then we'll plug it eventually into this expression for the displacement. But first, in the y dimension, I'm going to plug in the known values. We started at a height of 45 meters above the ground. Although this ball was thrown, it was thrown in a horizontal direction, meaning it had no vertical velocity, and so this goes to 0. Finally, this is usually plus 1/2 a, but I'm replacing that with minus 1/2 g because the acceleration due to gravity is the only acceleration of the ball, and it acts in the negative or downwards direction. Solving this for time, we get 3 seconds, substituting that into the initial expression for horizontal displacement, and we're going to solve it for the initial horizontal velocity, which is 10 meters per second. Question 34 depends on the formula that we introduced a few slides ago, and it's the one you haven't learned yet. So I'd like you to pause if you didn't know how to solve this question and use this formula. See if you can get the answer. Okay, hopefully some of you were able to get it on the retry, even if you couldn't get it the first time. This is really just a proportionality question if you knew which formula to use. So what's going on here? We're asked how to compare two things where the mass is the same, so this term is going to go away. 2 and pi are both constant, so they're irrelevant. And the proportionality that relates the period of something oscillating on a spring to the spring constant is that the period is proportional to the square root of 1 over the spring constant. Therefore, as the spring constant increases, the period decreases. Finally, we end with question 35, which asks us to determine how fast a satellite must be moving if we double its orbital distance. We'll start with the expression for gravitational force and set that equal to the sum of centripetal forces, because it's the only force acting on a satellite, and therefore it is the entire sum of centripetal forces, so it equals mv squared over r. We can solve this by canceling one r on each side. They're both in the denominator, but one will remain on the left. And the lowercase m, meaning the mass of the satellite, also gets canceled out. Rearrange this algebraically, and you get v is equal to the square root of gm over r. Since g and m is the mass of the Earth here, are both constants, the velocity is just going to change as a function of 1 over the square root of r. And so how much will the velocity change if I double the radius? It will be the initial velocity over the square root of 2. Here's the answers. I ask that you please email me. Tell me how many you got correct. It's not going to go in as a grade, so you don't have to lie about it. I just want to know.